Good morning friends. Today we are going to see, in this particular lecture, we have seen the heat conduction equation with heat generation in Cartesian coordinates in previous lecture. Cartesian coordinates. What is that equation? General heat conduction equation is d square T by dx square plus d square T by dy square plus d square T by dz square plus z by k is equal to 1 by alpha dt by dt. Now you know, in a space, the position of any point in a space, let us say this is a space, and in a space the position of any point, let us say P, is either given by Cartesian coordinate, that is x, y, z, or either it is given by spherical coordinate, this is Cartesian coordinates, or it is given by spherical coordinates. Anybody knows from the mathematics what are the spherical coordinates? Yes, you are right. It is r, that is radius. Sorry, before spherical there is cylindrical coordinates. Cylindrical, and finally there is a spherical coordinates. So either the position of the point, any point, is given by Cartesian coordinates or cylindrical coordinates and or spherical coordinates. The position is same, but only the method of indication is different. These are the different coordinate system you will learn in mathematics: Cartesian, cylindrical or spherical. So what is cylindrical? It's a radius of that point from some center point, some reference point r, then theta and z. What is theta? Angle with respect to x-axis. And what is z? Z means distance along z direction. So r, theta and z are the cylindrical coordinates. These are interconvertible. Because all coordinate system are doing the same job, indicating the position of a point in a space. And this is a spherical coordinate. In spherical coordinate there are two angles and one radius. So it is a radius, first angle with respect to x-axis and second angle with respect to, that is phi, with respect to z-axis. Radius from certain reference, that is origin, theta angle with respect to x-axis, and this is the angle with respect to z-axis. This is spherical coordinate. The purpose of all coordinate system is same, to indicate the position of a point in a space. So as this equation is in Cartesian coordinate, similar sort of expressions are present for general heat conduction equation in cylindrical and spherical coordinates. Now in the examination we don't have derivations for these two. We are having only derivation for this, and this I have already derived in the previous lecture. Okay. For cylindrical and spherical, might be in the examination they will ask only to state, to write only the expressions of general heat conduction equation in cylindrical coordinates or spherical coordinates. Okay. So I will give the expressions for general heat conduction equation in cylindrical and spherical coordinates. So what are these expressions? For cylindrical coordinates, Cartesians are x, y, z. Position is given by linear distances x, y, z. Now cylindrical coordinates. What are the cylindrical coordinates? One is the radius, other is angle with respect to x-axis, theta, and distance along z-axis is z. So one angle and two distances. One is the radial distance and other is axial distance. Along axis, this is along radius. So r, theta and z. So what is the expression? It is a modification of only Cartesian coordinates. These are the same equations, only the system, coordinate system is different. So what is this? It is 1 by r d by dr of r dt by dr. R dt by dr. This is the first, along the first coordinate, that is r, plus 1 by r square plus 1 by r square d by d theta d square t by d square theta plus d square t by dz square is equal to plus, now it is a case with heat generation. With heat generation means that term is as it is d by k is equal to 1 upon alpha dt by dt. 1 upon alpha dt by dt. Let's check it out. This is your first coordinate, 1 by r d by dr of r dt by dr. This is the first coordinate. What is the second coordinate? That is theta. This is the second coordinate. And z, d square d by dz square is indicating the third coordinate. The g by k is indicating heat generation term, and this indicates the unsteady state term, that is dt by dt is not equal to 0. Okay. Similar sort of expression exists for third coordinate system, that is the spherical coordinate system. Spherical coordinates. Okay. So that is r, radial distance, then angle with respect to x axis and angle with respect to z axis, r, theta and phi. So it is 1 by r square d by dr of r square dt by dr plus 1 by r square sin theta, 1 by r square sin theta d by d theta of sin theta dt by d theta. This is the first coordinate r, this is the second coordinate theta, and another coordinate is remaining 1 by r square sin square theta, 1 by r square sin square phi, because I am writing for third coordinate, d square t by d phi square plus heat generation z by k is equal to 1 by alpha dt by dt. This is unsteady state term. So this indicates first coordinate r, this second term is a little big term, that is theta, and this is third coordinate term, that is phi, plus z by k is equal to 1 by alpha dt by dt, that indicates unsteady state. So these are the equation 1, general heat conduction equation in Cartesian coordinates. This is general heat conduction equation in cylindrical coordinate, and this is the general heat conduction, that is equation 3 in spherical coordinates. Now in the examination there are no derivations for cylindrical and spherical coordinate, only they will ask the expressions, they will ask the expressions to write for you. Okay. Now you are saying, sir, which one we have to use for a particular analysis of a thermal system? When Cartesian coordinate, generally linear distances when we are using, when there is a case of wall or slab, linear distance. This cylindrical coordinate when we are using, generally when there is a case of pipes, that is a cylinder, okay. And spherical coordinate generally we are using when there is a sphere, that is what, hollow sphere or spherical case situation. So as I have already told, these are the standard forms. Okay, most of the thermal systems are either analyzed by considering it as a wall or slab, or considering it as a hollow cylinder, or considering it as a hollow sphere. So whenever wall like things are there, whenever there is a linear thickness or like that term is there, then you can use the Cartesian coordinates. Whenever there is a cylinder analysis, cylindrical shape analysis like pipes, flow through pipes and heat transfer across the pipe, then you can go for a cylindrical coordinate equation. When there is a case of sphere for the thermal system, then you can take the example of, you can use the expression of these spherical coordinates. All equations are same. All equations you can convert into one another. Okay, the meaning of all the expression is same. Only the thing is, depending on the shape of the thermal system, we are changing which expressions, we are choosing which expression we have to select for thermal analysis. That's it in this lecture.